Welcome to Architectural Insights with King-KAMBUF, and thanks for joining us on the Beyond the Comfort Zone Talking Shit with King-KAMBUF platform. This is where we take the most advanced intelligence from the absolute forefront of architecture, engineering, and planning. The kind of material usually locked away in PhD seminars or specialized research labs, and we break it down into real, actionable foresight.
Yeah, and today we're pulling everything directly from the Daily Mentorship Digest. This is the one for Monday, December 1st, 2025, provided by the services of KING-KAMBUF PS Architecture. Our whole mission today is to really synthesize this master's level stuff fast. We're taking research from all over, from the heat of Phoenix and Riyadh, the seismic zones in Taiwan, the huge logistical hubs like Rotterdam, and turning it into immediate insight for you. Whether you're a strategic designer, a builder, or a civic leader, this is for you.
And we're really not talking about static design anymore, are we? We're diving into forces that are, well, they're often invisible. Or at least they're treated like secondary concerns, things like thermal cycles, the subtle pull of a magnetic field, the shock wave from a helicopter's rotor-wash, even acoustic pressure. These are shifting from being just details to becoming primary design parameters.
They absolutely are. We're seeing the built environment evolve into this dynamic, active system. I mean, we're talking about buildings that can literally breathe, that brace themselves against climate, that integrate logistics and even political data in real time.
It's a complete paradigm shift.
It is. This is the definition of next-gen ACMP mastery. It requires you to stop seeing a building as a static shelter and start seeing it as a dynamic, responsive component within these massive interconnected systems. Systems that are responding, moment to moment to energy, to physics, to fluid mechanics, and even to data streaming from policy dashboards.
Wow. It sounds like we need to stop designing buildings and start designing these incredibly complex integrated organisms. Okay, let's unpack this, and let's start with the literal skin of the structure. That seems to be where the conversation between architecture and climate is happening most aggressively. We're moving into the dynamic envelope.
Architecture as a climate regulator.
Exactly. The first major trend we're seeing is that shift. The building envelope is moving away from being just a passive shield, something that just keeps the weather out. It's becoming an active, climate-responsive regulator, and it's a crucial adaptation, especially when you're facing these global extremes like relentless heat and punishing high winds.
The digest highlights three really compelling, almost sci-fi applications here. Let's start where the heat is at its worst. Phoenix, Riyadh, Perth. They're pioneering what are called aerostatic roof cushions for extreme heat. Tell me about these climate-reactive thermal lungs. What are we talking about here? The concept is actually surprisingly elegant. Imagine roof membranes that have these pressure-responsive gas chambers built into them. When they're hit with an intense solar load, the gas inside heats up and it expands. This causes the membrane to physically lift and swell. It's basically a controlled dynamic balloon system sitting right on top of the roof.
So the building literally puffs up to protect itself when the sun gets too intense. What are the benefits? I mean, this sounds incredibly complex and expensive. What's the payoff?
The benefits are substantial and they compound. First, that expansion gives you significantly more shading over the actual structural roof deck. That alone drastically cuts down your solar heat gain. And second, just as important, it boosts what's called thermal buoyancy. That big cushion of expanded gas acts as an enormous thermal bark, managing the air layer right above the building and stopping that heat from soaking into the structure below.
So it's not just shade, it's an active insulation layer.
Exactly. It transforms that passive roof into a climate-reactive thermal lung. It's highly efficient, but it introduces kinetic variables, movement, and that's where it gets tricky for a traditionally static assembly.
Right, and kinetic variables mean structural headaches. If I'm a structural engineer, the alarm bells are ringing about stress transfer. You've got this massive cushion expanding and contracting all day, maybe by inches, maybe even feet. What's the core structural challenge that Digest flags?
The absolute critical point is defining that roof-to-truss connection. You have to engineer a system that allows this cushion to expand, to move, to settle, all without creating overstress on your perimeter beams or the internal trusses. If you just use a standard rigid clamping detail, the thermal forces from that expanding gas will create dangerous localized stress. You're talking about a high risk of tearing the membrane or warping the beams over time from fatigue.
So the solution has to prioritize flexibility and controlled movement, not rigidity. You're looking for connection details that allow for things like micro-rotation or controlled slippage, right?
Precisely. It's an exercise in kinetic design, not static design. The solution involves these meticulously engineered connections. You're seeing sliding plates, high-grade polymers, maybe PTFE bearings, things that manage the movement instead of fighting it. You're designing for predictable movement, which adds a huge layer of complexity, but it's what allows the system to work safely for decades.
That distinction is key. Okay, let's switch from heat to wind, because not all these dynamic envelopes use gas. Some are using magnetism. This is the ferro-phase facades for high-velocity wind corridors. The research is happening in really severe wind zones, like Denmark, Taiwan, and Patagonia.
Right, so we're moving from thermal dynamics to electrostructural dynamics. These are composite facade skins, the panels you see on the outside of the building.
Yeah.
And they have these ferromagnetic lattices embedded right inside them.
So when a Category 4 typhoon is bearing down, or
Yeah.
a massive North Atlantic gale, what happens? What's the active response?
The building's central monitoring system detects wind speeds going over a certain programmed threshold. It then activates an electrical current, which generates a powerful, localized magnetic field that interacts with that lattice inside the panels. And this causes the panels to dynamically stiffen or brace up.
That's incredible. Building is literally changing its material properties moment to moment based on the load.
Yeah.
But again, let's talk trade-offs. This sounds immensely complex. Why do this instead of just building a massively thick, passively strong panel?
It comes down to resilience and efficiency. Instead of designing the whole structure for that 1 in 50-year peak gust with maximum passive resistance, which is hugely heavy and material intensive, you design a lighter system that only activates using minimal energy when the demand is actually there. It's smarter, it's lighter, and it's more economical in the long run as long as the system is reliable.
But reliability has to be the nightmare, right? If the panel itself is changing its stiffness, going from flexible to rigid, that transition has to create massive stress at the connection points. What's the structural weak point here?
The core conflict is defining the mullion anchorage detail, where the panel meets the frame. A stiffened panel transfers shear and moment loads in a radically different way than a flexible one. So if your mullion is designed for a flexible panel, and that magnetic field suddenly makes it rigid, you get this higher, sharper shear load transferred instantaneously. That connection is going to fail from shock loading or rapid fatigue.
So the connection itself needs to be dynamically tuned, not just the panel.
Exactly. The anchorage has to have elements that can handle that variability, maybe specialized rotational joints that can decouple the shear transfer during the stiffening phase, or viscous dampers that absorb that immediate spike in load. The magnetic field doesn't just change the panel, it changes the entire load path into the building's skeleton. Managing that transition is everything.
Fascinating. Okay, let's pivot completely. From resisting forces to actually harnessing biology for light. This takes us from high-tech materials into living infrastructure. This is bioluminescent street-edge mobility lanes. The pilots are in places like Seoul, Nairobi, and São Paulo.
Yeah, this one is really interesting. It targets those last-mile corridors, so pedestrian paths, bicycle lanes. They're cultivating microalgal bioluminescent paving elements. The goal is to dramatically cut the energy demand for night lighting by creating these living illumination systems.
It's beautiful in concept. I mean, zero energy consumption for lighting those paths.
Yeah.
But you're integrating a living, highly sensitive organism into aggressive, high-traffic civil infrastructure.
Yeah.
I can only imagine the maintenance challenges.
And that is the absolute crux of it. The core design challenge is proposing a paving section that can successfully balance three very conflicting demands. One, you have to maximize light emission from the algae, which means nutrients, oxygen, protection from UV. Two, you must have easy maintenance access to service that biological material. And three, at the same time, you have to maintain absolutely crucial zero-tolerance slip resistance for human safety, especially when it's wet.
Right, so you can't have this beautiful glowing path that needs a 3-person crew with a backhoe every week to maintain it, or one that becomes a huge liability because the nutrients you need to feed the algae make the surface slick.
And the design of that paving section has to be a masterclass in unified systems thinking. The physical parts, the substrate, the containment cells must integrate the biological needs with the public safety requirements. If those three things aren't designed in concert from day one, the whole system fails. It demands this seamless blend of bioengineering, civil safety, and structural durability.
The design brief is basically make it glow, make it safe, and make it last for a century. A tough ask, but probably a necessary one as cities push for zero-carbon infrastructure.
It is. Now let's shift our scope. Let's zoom out from the building envelope to the entire urban nervous system. This next section is about systemic infrastructure, how we're addressing mobility, resources, and critically, how policy is now being forced into these real-time feedback loops with the physical world.
Let's stick with that mobility theme first, but let's take it underground. Subsurface freight mobility. The digest is pointing to pilots in really high-density port cities like Rotterdam and Delhi. They're using magnetized tunnel skids to move freight.
Yeah, this is a direct response to gridlock and emissions. By creating a subterranean, friction-controlled transport field using magnetism, they're shifting that heavy logistics load into its own hidden network. It's faster, it's quieter, and it moves heavy goods without disrupting life on the surface.
And that's assuming you can even build the tunnels in the first place, which is a massive challenge on its own.
Yeah.
But let's set that aside. The design constraint seems to be all about optimizing the space inside that tunnel.
It is. The critical friction point is designing the optimal tunnel cross-section that has to balance three conflicting needs. Number one, the required freight clearance. How big is your cargo capsule? Number two, precise magnetic rail alignment. The whole system depends on micron-level precision for efficiency. And number three, necessary human maintenance access. You need safe, ergonomic space for crews to work in.
And all three of those are fighting for every last inch inside a very constrained tunnel diameter. The bigger the freight, the harder it is to maintain the rail alignment and the more dangerous it is for workers.
It's a trade-off matrix. Exactly. You compromise on clearance, your capacity drops. You compromise on rail alignment, the system fails. You compromise on maintenance access, the system becomes impossible or too expensive to operate. The optimal design requires intense simulation, modeling the cost of repair right alongside capacity and speed. It has to be economically balanced, not just structurally sound.
All right, from logistics to resources, let's talk about deep earth thermal borrowing. The pilots are in places like Reykjavik and Hokkaido. They're using thermal borrowing shafts to connect deep earth temperatures with district energy systems.
This is all about what they call geologic tuning. Deep down, the Earth's temperature is incredibly stable all year round. By tapping into that, the system can stabilize these huge winter heating fluctuations. It effectively makes the energy grid geologically tuned. The Earth becomes this massive, stable thermal battery. It can absorb excess heat in the summer and provide consistent warmth in the winter.
That offers huge energy security, especially against sudden cold snaps. But the challenge isn't the drilling, right? We can drill deep. The challenge is proving that this is sustainable and diagramming that really complex exchange of energy.
Absolutely. The designer's real intellectual challenge is to conceptualize and diagram that thermal exchange. And I don't mean a simple schematic. You need to illustrate the thermodynamics, the precise flow, the rate of temperature exchange, the stratification of heat capture between different ground layers, and how that all connects back to the fluids moving through the district heating loops.
That diagram has to show the geological budget, basically. You have to prove you can sustainably borrow that heat without depleting the local resource over a 50 or 100-year life cycle.
And that means complex modeling of subterranean fluid mechanics and thermal conductivity. It's essential for getting regulatory buy-in and public support. The diagram has to make that invisible process of thermal stability legible. It has to prove the long-term viability to stakeholders.
And finally, let's look at the highest level of integration, marrying physical systems with civic strategy. Governance-linked GIS twins for water councils. The intelligence here is coming from managing water basins in Ghana, Peru, and Croatia.
This is where urban diplomacy and hydrology completely merge. They're building these water governance GIS twins, digital duplicates of the entire watershed where real-time hydrologic data flow rates, contamination levels, soil moisture feeds directly into policy dashboards. Dashboards used by regional or even international water councils.
It's the ultimate policy feedback loop. So if the digital twin predicts a critical drop in flow because of a drought upstream, the policy dashboard doesn't just show a warning. It can immediately trigger pre-agreed policy actions like irrigation limits or emergency water transfers.
It shifts policy out of these quarterly reports and into continuous real-time response. But the political friction point is immense. Policymakers are not hydrologists. They need that data translated instantly and reliably into something they can act on.
Which means the core challenge is designing that crucial data-to-architecture interface. What is the tool that translates 78% soil moisture depletion in Subbasin C into a usable decision?
The interface has to bridge scientific complexity with political legibility. So you're translating vast, complex metrics into physical, visual formats. Maybe dynamic 3D models of the watershed showing risk zones in real time, or augmented reality overlays for field staff, or even simplified traffic light colored spatial dashboards for the council meeting. The challenge is making sure that simplification doesn't lose the critical nuance. If it's too abstract, they ignore it. If it's too technical, they misunderstand it. It has to be precise, immediate, and politically neutral.
So the designer is really acting as a translator between earth science and democratic action. That's a huge responsibility.
It is. And that actually brings us to our next section, where we transition from these specific global innovations to a single massive conceptual project, an RFP that forces the integration of everything we've been talking about, but in an extreme environment. We're talking of the Intermodal High Desert Innovation Exchange in the Mojave Antelope Corridor.
This scope, it sounds like an architect's dream, or maybe their nightmare. It's a massive integration campus that has to link 4 completely different elements: aerospace testing, desert ecology science, rail modernization, and public administration training, all in one place.
Just picture it. You need these heavy structural testing bays for new rail cars right next to highly sensitive desert climate labs, all while weaving in public-facing governance pavilions and multimodal transit studios. And the core difficulty is that extreme climate volatility of the desert, the heat, the temperature swings, the wind, coupled with the high sensitivity of the research and the public visibility of the governance work.
The suggested angle here is to frame it as a desert systems parliament, a place where extreme climate, mobility, and public administration have to converge and cooperate.
And that structural metaphor has to be made real. It can't just be a slogan. Which leads to the primary architectural challenge, conceptualizing a central atrium that physically expresses that necessary cooperation between the engineering innovation and the public-facing governance.
It can't just be a shared coffee shop then. The space has to actively encourage or even force interaction and understanding between these very different groups.
Absolutely. Think about the didactic potential. Maybe one side of the atrium exposes the raw engineering, the giant tension trusses, the data conduits, the thermal brake systems we just talked about, all visible and labeled. That represents the transparency of technical innovation. And then the other side might use more traditional human-scaled civic materials, recycled desert stone, quiet gathering spaces, representing the permanence and welcome of governance.
And the challenge is how you reconcile those two fundamentally different aesthetics and functions.
Yeah.
How do you integrate them without one just overwhelming the other?
The integration happens in the shared experience. Maybe the roof structure itself is the unifying element, a massive self-shading canopy that exposes that required cooperation. Or maybe the thermal regulation system for the whole campus is visibly routed through this atrium, showing how both the governance wing and the testing bays rely on the same shared infrastructure. You could have digital displays that blend real-time data from the aerospace testing with the regulatory policy being debated next door. The atrium has to be designed for forced, informed dialogue.
That's it. That structural expression of cooperation is what elevates it from being just a container to being a mission statement. Okay, let's look at the specific portfolio drills tied to this, starting with the High Desert Mobility Lantern.
This is a really demanding prompt. Design a vertical beacon structure for this desert mobility hub. But the core design goal is crucial. It has to capture solar intensity, wind stratification, and nighttime radiative cooling, and display those environmental forces as visual cues. The structure itself becomes the data display.
And the constraints force total passive reliance. It has to use passive systems only. The light transmission has to vary based on environmental stimuli, and, this is the killer, it must include at least one structural element that doubles as a climate sensor.
Right. This pushes the boundaries of material science and passive mechanics. If the structure is the sensor, you have to leverage that extreme diurnal swing of the desert.
Think about designing a vertical core where the structural steel is deliberately shaded, while the external fins are exposed to that 49 degrees Celsius daytime heat, that thermal difference.
The expansion and contraction of the outer material relative to the stable inner core, that can be harnessed.
So that thermal movement could be translated mechanically, maybe with levers or linkages, to open and close louvers, controlling the light transmission into the beacon.
Precisely. The movement of the structural steel is the data input. The resulting variation in light, the lantern's glow, becomes the visible output. It tells you the intensity of the solar load or the wind pressure without a single electrical sensor. It's architecture as a thermodynamic instrument.
And what about the wind stratification part? How would that work?
Wind stratification is just the changing velocity and direction at different heights. So the lantern could have wind-activated elements, specialized weather vanes, or lightweight tensile fabrics at different levels. These elements would vibrate or move based on the localized wind speed. And since they're attached structurally, they become these visible indicators of the wind profile, linking the vertical form of the beacon to the atmospheric dynamics.
That is a deep test of integrating structural integrity with real-time environmental display. Okay, the second drill. The stratified civic archive.
This one asks for a vertical public archive where each floor, each strata, corresponds to a different layer of history: geological, cultural, and political. So it's not just stacking floors, it's building a structural narrative.
And the constraints really focus on structural differentiation. No two strata can share the same structural system, the circulation has to act as a vertical narrative, and there has to be one civic space that blends them all into a unified hall.
This immediately forces the designer to justify material choice based on metaphorical weight. The lower geological stratum, focused on deep history and permanence, that demands structural materials that express stability. Heavy, earth-anchored concrete shear walls, maybe massive timber elements, things that reflect compressive strength and being rooted.
Then as you move up, you hit the cultural strata. History gets more complex, more interconnected.
So that midsection might use a complex articulated steel frame, maybe moment frames or braced frames, to symbolize that complexity and the dynamism of cultural exchange. And then finally, the upper political strata, dealing with contemporary volatility that could use light, high-tech tensile structures or lightweight composites, reflecting rapid adaptation and maybe impermanence.
The sectional diagram becomes a physical history book. But the real challenge is that unify hall. How do you bring those three radically different structural languages together in one harmonious space?
That's the test of architectural resolution, isn't it? The unified hall needs a structural element that transcends the individual systems. Maybe a massive, singular dome or ceiling plane that floats above the space, supported by elements from all three strata, but using none of their exclusive languages. And the circulation path, the vertical narrative, it needs to feature transitions that highlight the shift. A change in material underfoot, or a moment of compression as you pass from the steel stratum into the tensile one.
This whole section just reinforces that idea that structure is not just about resisting load anymore. It's about expressing meaning and managing these incredibly complex dynamic systems.
Exactly. And that's a perfect segue into our next section, which dives into the real engineering weeds.
This is the section I always find the most humbling. It's a deep dive into the forces that separate master-level practice from standard design assumptions. These are lessons from intensive RE study blocks, focusing on vibration, movement, and atmospheric effects that can catch even seasoned pros off guard.
This is all about understanding the granular physics of how a building interacts with its environment. These are forces that defy typical static calculations. Let's start with air and temperature, atmospheric and fluid loads.
Okay, let's start with a crucial life safety one, especially in dense medical districts. Rotor-wash uplift inversion zones on hospital roofs. We think wind uplift pulls up, but helicopters, they introduce a whole different load path.
This is critical. The lesson is that helicopter downwash, while it's a powerful downward pressure at first, creates this massive vortex that rolls back up when it hits the roof deck. This reversal of pressure, or aerodynamic inversion, creates intense, localized uplift right along the parapets and roof edges.
So the very spot where a designer expects maximum uplift from wind suction is the spot that gets hit by a totally different, concentrated upward pull from the helicopter's wake.
Precisely. That localized, rapid reversal of pressure can easily exceed the capacity of the roof membrane anchorage, especially the mechanical fasteners near the edge. The design workflow has to analyze this inversion and demand more robust, often doubled-up fastening, specifically in that zone around the helipad. It's a specialized, high-risk load case that standard code often misses.
That's a phenomenal example.
Oh.
Okay, next. Vent-driven uplift drift in large atrium bridges.
This one shows that air movement itself is a structural load. In these vast, super tall atria, you get the stack effect warm air rising rapidly. This creates a powerful, sustained vertical draft. And if it's large enough, that air movement translates into a micro uplift force.
So if you have a pedestrian bridge spanning that atrium, the sustained vertical draft can actually exert enough force to cause a subtle, persistent upward deflection, a drift at the bridge's midspan.
And while that's not going to cause a catastrophic failure, the deep lesson is that this vertical air movement has to be modeled as a sustained, non-uniform structural load. That sustained upward drift can lead to serviceability failures, cracking finishes, misaligned rails, or uncomfortable, high-frequency vibrations. For those beautiful, architecturally expressive elements, even a millimeter of unexpected drift is a design failure.
It's the silent, continuous pressure of air, like a tiny, omnipresent hydraulic jack. Okay, and within science campuses, we have intra-building microclimate drift. How does the climate inside the building affect the structure?
It's all about temperature gradients and expansion. A modern lab is a complex ventilation machine. Say one bay is running a furnace or a specialized exhaust for hours, drastically changing the air temperature in just that zone. This continuous operation shifts the temperature profile across adjacent structural bays.
And that thermal difference, even just a 5 degrees Celsius difference between Bay A and Bay B, is enough to cause localized stress.
Absolutely. That persistent temperature difference leads to thermostructural drift. One steel frame is expanding slightly more than its neighbor, which introduces unexpected shear and bending forces on the connecting beams. The structure is essentially trying to pull itself apart hour by hour. This forces designers to consider expansion joints designed specifically for these small, sustained internal thermal differences.
The structural engineer has to be talking to the HVAC engineer who's talking to the process scientist. That's real multidisciplinary integration.
It is. Now let's shift gears from the subtlety of air to the sheer violence of vibration, impact, and torsion loads.
Okay, moving to high-density residential towers and the structural consequence of just daily life. Staggered occupancy vibration stacking.
In these massive mixed-use towers, the amenity floors, the gym, the lounge, the laundry, they all activate unique rhythmic vibration patterns. A treadmill has a different frequency than a commercial dryer. The structural risk is that these unique patterns, when they're all happening at once at different heights, can align at specific low-frequency resonance points.
So the vibrations don't cancel out, they actually amplify each other.
They constructively interfere, exactly. The lesson is the necessity of mixed-use resonance analysis. The building needs isolation systems, like specialized damping pads or floating floors, that interrupt the transmission of these rhythms. The goal is to make sure the combined vibrations don't exceed human comfort thresholds for the residents. In these ultra-luxury towers, human comfort is the critical failure threshold.
Now for a really violent industrial load, container impact torsion scatter at port terminals.
A port terminal slab is just subjected to brutal, unpredictable forces. When a massive container is set down wrong, misaligned, dropped a little, it introduces a sharp, non-uniform torsion pulse into the deck slab, a twisting energy that radiates out in an unpredictable pattern.
And that is exactly the kind of dynamic twisting energy that causes catastrophic shear failure at slab edges and column connections if you only designed it for static vertical weight.
The workflow has to include analysis of impact frequency and what's called port vibration zoning. You have to massively reinforce the deck slabs in those impact zones with high shear reinforcement and specialized detailing to resist that scattered torsional energy.
We also see this rhythmic vibration in more mundane places, like blade-induced slab flutter at wastewater facilities.
Yeah, facilities that handle fluids often use oscillating screens or massive pumps. These things produce a predictable, continuous rhythmic vibration, a hammer effect. The lesson is that this repetitive hydromechanical action has significant structural resonance consequences for the nearby slab bays.
The continuous rhythm causes the concrete slab to oscillate or flutter, which could lead to long-term fatigue in the concrete and rebar.
So the mitigation is either structural isolation, the machinery sits on a completely isolated pad, or you have to tune the slab's natural frequency so it's well away from the operating frequency of the machinery. The engineer has to anticipate that the operational tempo of the equipment will dictate the stiffness of the surrounding structure.
And finally, a really interesting one for museums with kinetic art: motion envelope vibration zoning.
This is a fascinating intersection of visitor experience and structural performance. A large, moving piece of kinetic art influences how patrons perceive floor vibration. If there's a huge, slow-moving pendulum overhead, visitors are sensitized to movement, and any perceptible floor vibration, even if it's tiny, feels magnified and unsettling.
So the structural analysis has to treat visitor comfort as a critical vibration behavior design parameter.
Absolutely. It involves defining specialized motion envelopes for where kinetic art is allowed, and then ensuring those specific floor plates are designed with extra stiffness and damping. The goal is to eliminate any secondary vibrations that might distract from the art or, worse, make people feel insecure.
That's a fascinating constraint, engineering the structure to manage the patron's psychological state.
Yeah.
Okay, let's move to the last set of these specialized loads, specialty structural and acoustic loads.
Let's start with nature as a structural component. Root matrix shear anchorage checks for stormwater bioswales.
We know bioswales are crucial for hydrology, but we rarely think of them as structural elements, do we?
We should. The lesson here is that the root density directly affects the soil's shear capacity. If that root matrix, the dense mesh of plant roots, fails, the soil loses its stability, which then impacts the performance of the adjacent pavement or walking paths. This concept of vegetation-soil coupling is fundamental for controlling lateral soil movement.
So the civil engineer needs to specify the type and density of the vegetation based on its root structure, treating it like a natural shear wall, not just a planting requirement.
Precisely. The plant life is acting as structural reinforcement. You have to ensure the vegetation density is sufficient to provide the required lateral stabilization to protect the adjacent infrastructure.
Now for the subtle world of acoustics. Curved surface echo torsion modeling in performing arts halls.
Performing arts halls use these complex curves to scatter and focus sound perfectly. But sound is energy, it's physical pressure. And those curves create echo clusters that redistribute acoustic force onto the structural ribs or shell elements.
So if the sound pressure is repeatedly concentrating on one specific architectural curve, that curve is transferring a localized physical load onto its supporting structure.
Yes. It's subtle, but it's a relentless physical force. This requires detailed modeling of acoustic pressure hotspots, basically mapping where the sound energy physically concentrates, and then providing rib stiffening in those areas. The structural ribs need to be locally strengthened to prevent microfatigue or high-frequency vibration induced by that focused acoustic energy.
That means the acoustic consultant and the structural engineer have to be sharing their 3D models and pressure mapping. True integration. And similarly, in big university lecture halls, there's lecture cycle acoustic drift.
This just reminds us that human presence is an acoustic material. Repetitive, high-density occupancy shifts the acoustic absorption and thermal patterns of the room radically. When a 500-seat hall fills up and then empties, the change in absorption and air volume is huge.
And that rapid shift affects how the HVAC and AV systems need to function.
Absolutely. The air handling needs to adjust to the thermal surge of 500 people, and the AV system has to compensate for the change in acoustic absorption from 500 sets of clothing and bodies. It's a dynamic operational load that has to be factored into the mechanical and architectural detailing.
And finally, a really cool transportation load. Compression shed slab design in steep inclined funicular depots.
This is pure inertia. A funicular car is moving fast, and it's incredibly heavy. When it decelerates at the depot, especially on a steep incline, the inertial forces don't transfer as a simple vertical load. They shift unexpected, high-intensity, non-uniform compression forces into the loading slab.
So it's a dynamic impulse load that tries to buckle the slab right where the braking system locks in.
Exactly. The slab design has to explicitly account for this transportation inertia using compression shedding details and localized reinforcement to handle those sharp, non-uniform stresses. It proves that transportation systems produce these highly specific, local dynamic stresses that are often missed if you only design the slab for the static weight of the parked car.
Wow. Okay, this final section really brings it all home. We're looking at specific engineering scenarios and safety codes dealing with all this dynamic energy.
Right, these are real-world case studies where new equipment revealed non-traditional risks and how engineers developed precise workflows to fix them. Real-world lessons.
Let's start with a major one for renewable energy retrofits. Thermal cycle truss relaxation.
The scenario was a research hangar. They put up a large solar array, a surprisingly light load, only 6.4 psf. But then they reported thermal cycle truss relaxation, a very subtle but critical displacement of 2.6 to 3.2 millimeters at the truss mid-panel. The culprit was the daily temperature swing from 18 to 49 degrees Celsius.
Wait, 6.4 PS is nothing. The structural integrity was compromised because of the temperature, not the weight.
That is the core defining lesson. The load is thermal before it is physical. The intense heat absorbed by the array, which then radiated directly into the steel trusses below, caused these significant expansion and contraction cycles. That daily 31-degree swing led to subtle, sustained fatigue and eventually permanent relaxation, a slight, irreversible lengthening of the truss elements.
I can just imagine the engineer's face realizing the failure wasn't the dead load, but this relentless thermal flexing. So what was the workflow to stabilize it?
It was highly targeted. First, they mapped the thermal gradients across the steel to find the exact hot spots. Then they added thermobrake shims non-conductive material under the solar array rails to interrupt the heat pass. Crucially, they also introduced secondary pre-tension tension rods to actively absorb those expanding cycles, giving the thermal expansion a controlled place to go. And finally, they detailed the truss connections to allow for controlled micro-rotation, preventing stress buildup.
That is a masterclass in treating thermal energy as a structural load. Okay, next, inverter-pulse torsion surges in a renewable energy facility. Here, electrical equipment is physically destabilizing the building.
In this case, the facility reported inverter-pulse torsion surges, a measurable 3 to 7 millimeter movement affecting adjacent steel moment frames. The source was high-frequency electrical switching in the inverters, ranging from 240 to 600 hertz.
And the lesson is so direct. Electrical equipment is a structural actor. The high-frequency switching creates mechanical vibration, which transfers into the slab and excites the steel frames as high-frequency torsion waves, a twisting energy.
So the mitigation was a merger of electrical and structural analysis. First, they had to identify the precise torsion surge harmonics, the exact frequencies causing the sympathetic twisting. The solutions included adding specialized rotational dampers, like little shock absorbers, to targeted joints to dissipate that twisting energy. They also installed vibration isolation bases under the inverters and introduced braced frame outriggers to stop the torsional energy from propagating through the whole building. They had to tune the building structural frequency to avoid resonance with the electrical system.
That's incredible. It highlights that in a modern facility, the building frame has to handle electrical noise not just as an EMI problem, but as a direct mechanical load.
A third critical scenario is rapid protocol thermal pulses in municipal command centers.
This speaks to continuity of operation during a crisis. When emergency equipment backup generators, battery banks, suddenly boots up, they generate these short-term, intense bursts of heat.
Exactly. And these thermal pulses affect the surrounding materials, particularly wiring trays and critical electrical systems. So the design for a command center, which has to stay operational at all costs, requires explicitly evaluating thermal surge pathways. You have to design pathways that isolate critical systems from the thermal byproducts of their own emergency operation.
And how are safety codes adapting to these dynamic risks? Let's start with NFPA 85M5 battery storage fire separation drift zones.
This is fire safety meeting material kinetics. NFPA 855 now dictates that your fire safety zoning has to account for dynamic movement. Specifically, the separation distances between battery cabinets must include drift allowances.
Because the high-density battery cabinets generate massive heat during peak charging, which causes thermal bowing, they physically shift by several millimeters.
Right. And if they bow inward, they reduce the required fire separation distance, potentially compromising the fire suppression system. The lesson is that clearances have to be verified under the worst-case thermal scenario, not just their static room temperature position. You have to budget space for movement.
And finally, from IBC 1618, Foundation Uplift for Counterslope Buildings. This is a big one. Uplift isn't just a roof problem anymore.
It's a profound site geometry lesson. If your building is on a counterslope site, where the topography rises up against the prevailing wind, it creates unexpected aerodynamic behavior. The wind hits the slope, flows rapidly upward, and generates a massive suction or vortex that can create uplift forces on the uphill foundations during high winds.
So the structure's being pulled up on the windward side, even if it's a multi-story building. And that site is traditionally only designed for compression.
It necessitates tie-down anchorage verification for these partial exposure zones. You have to design the foundations to handle uplift load cases, even on the side you'd think is in compression. It proves that complex site geometry fundamentally alters wind behavior.
We have covered an incredible amount of terrain today. From the subtlety of microalgal illumination and magnetized freight to the intense consequences of thermal cycling and inverter pulses. We looked at how aerostatic cushions turn roofs into thermal lungs and how ferro-phase facades dynamically change their stiffness.
And we synthesized the immense complexity of integrating all of it into a single vision with that High Desert Innovation Exchange RFP. The core mastery required of you, the listener, is in understanding those invisible forces, the thermal, the torsion, the fluid, the electrical, and translating them into predictable structural and service behavior.
So what does this all mean? It means the future of design demands a designer who thinks like a climate scientist, a logistics expert, a data translator, and a structural engineer, all at the same time. We're moving so far beyond static form into active, responsive, adaptive systems that are in constant conversation with their environment.
The critical insight, the one that really defines future leadership in this sector, isn't just reacting to these forces and resisting them, it's about using them. It's designing a system that makes the environment work for you. So we'll leave you with this idea to mull over, synthesizing the most advanced thinking from the Daily Mentorship Digest. How can I convert hidden forces, thermal, magnetic, fluid, electrical, into architectural foresight, shaping design intuition rather than simply reacting to disruption? Can I design a system that, like the mobility lantern, makes the load visible, or like the ferro-phase facade, makes the resistance adaptive?
Use this intelligence. Review your current projects. Sketch out a concept for that high-desert mobility lantern or the stratified archi, and begin viewing every vibration, every temperature gradient, and every policy shift not as a problem to be resisted, but as a critical design input. Your mastery expands with every unseen force you can anticipate.
Until next time.